Okay. So, good afternoon, everybody. So, I'm happy to welcome you to this seminar, our condensed matter seminar at the East African Institute for Fundamental Research. The seminar will be given by Professor Gian-Marco, who is a professor at the Université Catholique de Louvain in Belgium. Okay. So Professor Gian-Marco, he has a doctorate in applied sciences, and he works mainly in the area of material science. Okay. So theoretical condensed matter applied to materials. He's one of the major developers of the ab initio code. Sorry, the ab init code. Ab init code. And the code can do quite a number of things. Kappa Renolo MD, your regular GFT, GW, and calculates optical and spectroscopic properties of materials also. So today we're happy to have him, and he'll be talking to us about their efforts to be able to develop new materials using the methods of using ab initio methods, but in the context of high throughput calculations, data mining, and a little bit about machine learning. Okay, so Gian-Marco, thank you.
Thank you. Thank you very much for the very nice introduction. So the title of the presentation was given, and as was pointed, I'm into material science, and as you may know, materials are one of the key drivers of innovation. So we want to have faster computers, more compact energy storage, for instance, more compact data storage, more efficient solar cells. And at the heart of all these improvements that are required, we need new materials. The question is, how can we find new materials with some specific properties in our information age? If I were to ask around me, I would probably get people telling me, oh, go on Google, and let's say that I'm interested in batteries. They would hope that maybe we can just type, okay, I'm looking for a good battery material, and then get an answer. Of course, it doesn't exist for the moment. If I were to ask that to my students, they would probably say something like, okay, I'd like to have a material that is between 3 volts and 4.5 volts. It has a good stability, and it has a good lithium mobility. And that still doesn't exist. And the problem with that is that we have very little information about the material's properties. About all the existing materials, we know very little. If I just focus on the inorganic compounds, there is roughly 50,000 to 70,000 materials. And among all of them, we only know the dielectric constant for 300 or 400 of those. We know the elastic constant for about 200 of those, the band gaps for 200 as well. And if I put all together all the encyclopedia that are available in the world, even on the web, I basically have a coverage for every property that is below 1% coverage. So if I were to come in Kigali and I would like to travel, the map that I would have is not like the one that you're just seeing now. If I have a 1% coverage, a 1% coverage is this. So basically, I would get lost in Kigali. And in fact, we materials designers, we often operate almost in the dark. We know very little about the materials. And so how do we work? We often work by trial and error. And that's what Edison did when he had to choose the filament to put in the bulb lamp. He tested basically 3,000 materials, one after the other, and in many cases it failed. Luckily for us, we have made some step forward thanks to ab initio calculation. And we are now able to compute the properties of materials even before the material is created in a lab. And so we've reached a level of maturity where this ab initio calculation can be used to do what is called high-throughput material screening. So what's the idea? Basically, the idea is that we consider very many compounds, typically thousands to hundreds of thousands of compounds. And for each of them, we compute first a property. If it fits our needs, we move to a second property. If that fits our needs, we compute a third property, and so on and so forth. If it doesn't, then we throw the material in the dumpster, just like Edison was doing the experiment. So he wanted a material with good properties, And he tested these 3,000 materials. In many cases, he put them in the dumpster. And in the end, he ended up with a material that was not the best. In our case, we hope that by testing many more materials, we'll be able to identify, let's say, 10 to 100 of compounds that would be used by experimentalists. And the idea is that one of the properties that we will have computed is to make sure that the compound is stable and that it has the good properties. And so basically we are saving some time and some money compared to the trial and error process. So what I showed you here, this process of testing the material, computing very many properties one after the other, and then throwing some stuff in the garbage, this requires to do these high throughput calculations because we're going to run thousands, hundreds of thousands of calculations. So this is the high throughput. Now, the good thing now is that everything that I've thrown in the dumpster is not lost. I can do some data mining with that and use that to predict other stuff about the materials. So in my presentation here, I'm going to try to show you what can be done with this approach of high throughput and then using data mining. Let me start by an example, which is the so-called transparent conducting materials. In many applications, you require a material that is both transparent and conducting. If I take the example of the cell phone, the material that is used for the screen needs to be transparent because I want to see what the screen is showing, and needs to be conducting because when I push on the material, there is something that's going on. There's a current that is flowing. In the same way, in a solar cell, I want the ray of light to go into the photoactive region, so that the upper layer needs to be transparent to the light. But then once I've created the electron hole pairs, I want to separate them, one at the anode and the other one at the cathode. And so the material needs to be conducting. Having a material that is both transparent and conducting, that's kind of having two properties that are antagonistic. And so it's not straightforward to obtain that in a single material. A typical high throughput approach, an ab initio workflow, would look like the following. So you have a bunch of structure, then you compute their stability, you make sure that they are transparent, then you want them to be conductive, and often to be conductive, you need to dope them, as I will show. So to be transparent, you will ask the material to have a wide band gap, because if you have a wide band gap, then the photon that is absorbed is above the optical range. If you want to have a good conductivity, you see that the conductivity is related to the mobility, and the mobility in terms is related to different things, but among others, it's related to the effective mass. And so if we look at typical oxides, they often present these kind of band structure. You have a conductor.
Gian-Marco.
Yes.
So I see this funnel. So I think it's important that you order the properties in a particular way, right? Like you don't start with dopability or conductivity, you start with something that's easy to do.
You're
right?
perfectly right, and that's very important. So there may be switches. Actually, the funnel that we use is slightly different from this one. Okay. But what you want to do is to compute, because at the top of the funnel, you're going to compute very many materials. And so you want something that is easy to calculate, because otherwise you're gonna kill your computer because doing too many very demanding calculations. So you're perfectly right that the dopability is something that you want to do at the end, because dopability requires to do defect calculation, which are demanding in terms of CPU. And so typically, just to answer also your question, we switched these two. We first started by the conductivity, because the effective mass is something that you can compute very easily from a DFT calculation. A band structure is very easy. The transparency, I mean, if you stick to the DFT LDA GGA, then that's okay. But as you know, the gap is underestimated. And so maybe you may screw the transparency. So we basically switched this order in the calculation that we did, and we'll show the results afterwards, okay?
Okay, sure.
So
yeah, thanks.
You're perfectly right. This is really important. That's one of the important point of a study, is to set up the brightest funnel, in the sense that you want to compute the property for many materials, those that are not very demanding in terms of CPU time. So you want to leave the most demanding ones at the end, and this is why they're called refinements often.
Okay, yeah, thanks.
Okay, you're welcome. Don't hesitate to interrupt. Huh? So I was saying that for the conductivity, we looked at indeed the effective mass, and that for typical oxides, the band structure looked like this. You have for the conduction bands a very low effective mass for the electrons, because the band is very dispersive. In contrast, at the top of the valence bands, you often have oxygen p character with a high effective mass. And as a result of that, many materials, as I will show, have a good mobility in terms of n-type, but a very bad mobility in terms of p-type. So next, to get the conductivity, we also need to have a certain amount of carriers, and for that, we dope the material either n-type or p-type. And as I just said, basically, because of the point that I was making about the difference in the curvature of the valence band and the conduction band of typical material, most of the n-type have a very good mobility. And typically, if you look at your cell phone, you're going to have indium tin oxide, which is an n-type transparent conducting oxide, as the layer of your cell phone. In contrast, the p-time, as you see, there's a factor of 10 here in terms of mobility. So they're much worse in terms of mobility. And this is very limiting for many technologies. If you think about transparent electronics, that would help you, for instance, do things like these, where you see through your computer to detect the surroundings without going through because there is some application like that go through the camera of your cell phone. If you just want to see through the cell phone, you want to have transparent electronics. And transparent electronics requires to have a CMOS, complementary MOS, which means that you have both N-type transistor and P-type transistor, and so you really need to have both. So efforts need to be done to improve the mobility in these materials. So the question that we tried to address was, can we find some good P-type candidates for such application? Is it searching a needle in a haystack, or maybe can we find the needle in a limited amount of time? And that's what we did using precisely the funnel that I was showing before. And the first thing, as I said, that we did was to look at the effective masses. By computing the effective masses, which is not very complicated from DFT, you can screen and remove very many materials and then focus on the more demanding calculation. And so typically we screened about 7,000 binary, ternary, and quaternary oxides. And in the end, one of the best candidates, we found many different things, but one of the best was this double perovskite, which has a low effective mass, typically 0.4, 0.5. It has a high valence band maximum favoring the P character, but that's dispersive. And since we had a limited number of candidates, we can even do the GW calculation to predict the gap to be 3.8, which is above the optical region, and so that's completely transparent. And so thanks to that, we managed to convince some of our colleagues to try to synthesize this material, which they did. And as you see, they doped it with potassium, and they checked that it was the correct structure. And then afterwards, of course, they checked that it was transparent, which is, as you can see here, the case. And also in terms of conductivity or mobility, more precisely, you see that these are the typical P-type material with this 10 square centimeter per volt second. And our new candidate basically is 3 to 4 times more mobile compared to those. So you see that by doing this kind of funnel approach and doing high throughput calculation, you can find materials with targeted properties. And typically, as I was saying, based on these high throughput approaches, there's been many databases that have become available online. I'm mainly working with the materials project, which is here, but there is also a NOMAD in Europe, which I'm starting to work with. And there is also the materials cloud of Nicola Marzari here. There is AFlow in the US, OQMD in the US also, and there's other databases. And there's even experimental databases like the COD, which is open completely. But most of them are completely open, actually. For the time being,
so yes, how do you, go ahead. So to choose your starting structure at the top of the funnel, you just go through all these databases, or what do you do?
That's basically the idea, yeah. In our case, we focused on a materials project, but if you want to have more candidates, you may try to go through all the databases. But in the end, I mean, most of them start from the ICSD. So they started from the ICSD and then relax the structure. So there's many duplicates when you look at all those databases. Okay. Thanks.
Yeah.
And so basically that's actually where I was heading to. I mean, if you want to interrogate those databases, you need to learn their API. Each of them can be interrogated through what is called the REST API. So that's an interface. And so you can basically ask questions, queries to the different databases. Each of them has a different way to interrogate them. So just to take an example here, I'm showing how to query the SiO2 structure in 3 different databases. There's a COD, the materials project, and the A-flow. And you see that that's very different. So the way in which the syntax that you need to use to interrogate the different databases is very different. And so if you want to interrogate all of them, it may quickly become a nightmare. Not only because the queries are different, but also because the responses are different. So you see that each of the different databases responds with a format which is different. So a few years ago, we had the idea that it would be nice to have a common API to all these databases. And so we started a series of conferences, the last one being in June this year, where we finally ended up with the release of the version 1.0 of the so-called Optimate API. It basically connects all these databases. So now, we just released it at the beginning of July, and now people are implementing the interfaces. There are some working examples. I'm not going to show them here, but that's something that is going on. Okay, so that's about the different databases that are available. Now, if we look into the different databases, of course, most of them are theoretical calculation from ab initio calculation, and the time that you need to compute a given property depends on the complexity of the property. So if you look at the structure, the chemistry, the band structure, that's a limited amount of time. If you start looking at properties like elasticity, piezoelectricity, the amount of time that is needed to get those properties is much bigger. So not surprisingly, if you look into the databases that I was showing before, there's a lot of information about the structure, a lot of information about the chemistry, the band structure, but very little about elasticity and even less about piezoelectricity, okay? And in particular, one of the things that we are interested in is the stability of the material as a function of temperature, because you want to know at a given temperature what's the most stable polymorph, because maybe you predict that one polymorph has the interesting properties, but if that's not the stable one, then you're screwed. So you really need to pay attention to that. So at t equal to 0, most of the databases that I was showing before have tools to show you which is the most stable polymorph, just based on DFT calculation of the energies of the different structures. Now, if you want to go above 0, then you have to take into account the vibrational entropy. And to do that, you need to do DFPT calculation. And this is very demanding. And so this is something that we started doing a few years ago. Basically, we developed a workflow to do high-throughput calculation of phonon. So basically, you provide the structure to the code. In this case, it's ab init. So then the code does the auto-parallelization, does an SCF calculation, then it computes all the perturbations that are needed to compute the phonon, merges everything, and then finally produces the database that is going to be, and analyzes the database to get all the properties. And then all the properties are inserted in a database, which is the materials project. And if you go online on the materials project, you will see things like this, where you can have the phonon band structure of the material. And if you click on a given Q point and a given band, you will be able to see how the atoms move for that particular wave vector and for that particular band. And then, okay, here the workflow, there's some cleanup. Basically, we computed the vibrational properties for 1,521 semiconductors. All that were released openly on scientific data. And as I said, it's all available on the materials project. But as I said, it's only for 1,500 materials. So that's not very much, okay? And this is where using machine learning may become handy, because precisely in the databases, we have little information about, the most demanding properties. And so it would be nice if we could use machine learning to learn from what we already have there, to extend that to many more materials and still use a funnel there, but then with something which is done by machine learning rather than computed from high-throughput calculation ab initio. So what is the idea of machine learning? Basically, you provide a collection of data that is called the training set, and each of these data points consists of a series of attributes which are labeled from x1 to xn. And then there's a value continuous y that is assumed to depend on those attributes. So for instance, it can be the entropy of my crystal, and the x here can be properties of the materials that I know already. It can be the mass of the atom, it can be the composition. I will show example later on. And from there, you would like to find a linear or non-linear model that gives you y based on what you know of the material. So again, maybe I can get my vibrational entropy from a series of properties that I already have about that material. Okay? So the way that it's usually done is we have this training set here, and then we have a test set that is used to determine the accuracy of my model. Did I do something that's predicting things correctly, or is it predicting things with a big error? Okay? So typically, the way that it's done is for a given database that I have, this collection of data points, I'm going to divide it into a part that is going to be called my training set. And then there's a part that I will leave for the testing. And so these are built to, these are used to build and validate the model. So the idea mainly is that we want to reduce the dimensionality of the point. So here you see, I may have many attributes for my different systems. And so what I want is to reduce that, because otherwise I won't be able to develop the model. So typically, it reduces the cost of the analysis by reducing this dimensionality, but it also reduces the noise. So if we look at this picture here, you see that there is many small pixels, but if I kind of simplify my picture into that, I have removed part of the noise. But at the same time, I would like not to simplify too much, so not reduce the dimensionality too much, because otherwise I will lose the main feature. If I, at the end, if for instance I say, okay, I'm going to just have one pixel for all that, it's going to be either black or white, but I have lost all the information. Okay. So this step that consists in reducing the dimensionality there is called feature extraction. For our atomic structure, this is really a crucial point. And so people have started developing ways to characterize a given structure. So the idea is that you are transforming the structure that you have into a bunch of numbers. So the x's that I was showing before, that basically tell you this is this structure, okay? And so there has been different methods around. I will be here mainly focused on two of them. One is the so-called MatMiner, which is available online freely. And then there is Magnet, which is also available freely online, okay? So both these approaches provide you a bunch of numbers that characterize a given structure. If I look at MatMiner, what it does is that it's gonna give me x's that are based on the composition, the structure, and the size. So in terms of composition, for instance, it's gonna give me the fraction of the different elements, the mean atomic mass, the mean atomic row. It's gonna give me stuff about the stoichiometry, about the electronegativity, and so on and so forth. It can give me information about the structure, the space group, the crystal system, the radial distribution, the bond fraction, the Coulomb matrix, and many other stuff. And finally, stuff that is very local, the site. So it can give me the radial environment, the motive attaching. So it can tell me, for instance, the atom here is in a tetrahedron, an octahedron, or the BCC environment, okay? So I can generate basically lots of x's for a given structure based on this. The other approach is called Magnet. Basically what you provide again is the structure, and out of the structure, it uses what is called a convolutional neural network to kind of encode the structure into basically a 96 number. So that's what you get at the end here. So these are the so-called magnet block, and one of them is 96 features that can be used to train a model afterwards. So that's the part that is trained here. And you see that it's being trained on the formation energy of roughly 70,000 data. And the mean average error for those data was about 28 millieV per atom. So you see that it's very good. And they used the same thing to train a model for the gap on less data because many materials have no gap, so they didn't use those. And so they ended up having also a very good accuracy with an error on the gap of 0.3 eV. Okay, so what was interesting about this MedNet is that you just provide, in fact, the position of the atoms and their type. That's all you provide. You just provide a CIF file, basically, with the atom position and the kind of element. And basically, by training this neural network, so this part, it was found that if you were looking at the correlation between the, if you want, the numbers that represented the different atoms, if you try to look at the Pearson correlation, and I'll get back to what is Pearson correlation later on, if you look at the correlation between those, you see that basically it follows the Mendeleev table of elements. So basically the neural network has learned just by being trained on these 70,000 materials, he has kind of learned the chemistry of the materials, okay? So this is really—
Yeah, so like that, the data used, was it experimental or computational?
No, in this case, it was computational.
Okay.
Because there are not very many experimental databases for which you have this many number of points. Usually, and I will get to that, the experimental databases are small, okay?
Okay.
And even in the case of theory, as I was showing before, you know, most of the databases that are online, the places where they have a lot of information is for simple things like the energy, the band gap maybe, but not for the phonons. You know, we have only 1,500, not for, you know, complicated stuff, okay?
Okay, yeah, thanks.
You're welcome. So to do stuff correctly, so you will have to train, and then you will have to evaluate your model and finally test it. So the way it's done is that, as I said in the beginning, you basically separate the stuff into your training data, your testing data. So basically you train, so you choose the features, then you machine learn, and then you get a model which you evaluate on your test set. If that's not good, you have to go back to the feature extraction or to the model. So you have to play with that, so to develop something that is working. And in the end, what you aim to do is to have a predictive model which can be used on new data, okay, in such a way that I can use this in my funnel to predict some property and then choose some materials, okay? So there's been a bunch of models that have been used, and I'm going to propose you here a few, it's an introduction to some of the typical models that I use to do machine learning. So the most easiest one is the so-called decision tree. So the idea is quite simple, is that if I want to sort, in this case, fruits, I will select one feature and say, okay, based on the color, I'm going to separate those that are green from those that are yellow and those that are red. If I look at all those that are green, I'm going to separate them based on the size. I want the big ones, the medium ones, and the small ones. If it's green and it's big, then it's a watermelon. If it's green and it's medium, then it's an apple. Green and small, it's grapes, okay? Same for the yellow, we can have the shape. And sometimes we need to introduce a further layer, okay? So you see that depending on stuff, you can classify everything, and you have different levels for the questions that you ask, but in the end, you end up with one particular case for each of the choices that you made in the tree, okay? Now, the most common and most easy thing to use to do machine learning, that's what is called random forest. A random forest is simply a bunch of trees like the one that I was showing before. So this is a decision tree. A random forest, a forest is made of trees. So you have many trees, and they are random in the sense that basically you change the order of these levels, okay? You change the order quite randomly. So you generate a bunch of different trees at random. And then for each of them, you look at the results, okay? And so if I want to see what's the result of this random forest, here I have 5 trees in my forest, I have to make choices and look at the result of the choices. So here, there's a coloring scheme that the yellow is so the places by which, so if you look at the brown thing, that's the line, that show the decision. So for instance, if I ask the first question, the answer is going to be this brown thing. And then if I ask the second one, the answer is the brown thing. You see that here, in this case, I go here, and then here. So if I look at the different results, in this case, it's red. In this case, it's red. There it's red. There, the last one is red, but this one is green. So in most of the cases, it's red. So the final prediction is going to be red because the majority is red. Okay? So this is the way in which a random forest works. Okay? Another important kind of model, and I guess that you've heard of that, that's the so-called neural network. So the idea is also quite simple. So you have, remember the axes that we had before, you basically take a linear combination of all the axes, you apply some kind of function, which is called the transfer function. And this is the function that basically brings the non-linearity in the model because all this is linear. And then out of the F, you get an output. So that's the most simple neuron. You start from the different axes, you mix them, and you apply a transfer function. Of course, you can have several neurons and add from the results of the first mixing. So you do 3 different mixing here, for instance, and the mixings are again mixed together. And you can repeat that several times. And these are the so-called hidden layers, because in the end, you have the input and the output, which is the result of the mixing here. So the only things that are needed to define the model are just the weight that you put here and the choice of your transfer function. Okay, so this is a neural network. So as I said, one important step in this development.
I have a question. How do you determine the weight?
So I don't. So there are algorithms that are available. So if you use Python, for instance, typically you have algorithms that do that. So the idea is to minimize the error that you make. So because you have a training set, so I have a bunch of points for which I have the X's and I have the Y. So what I do is that you put some weight and then you compute the Y's that are resulting from some starting weights. And then you do a minimization of error in the least square sense to optimize the weight. That's what the algorithm does. I haven't developed that. I'm using tools that are available to do that. Okay.
Okay. Thank you.
So you have many points for which you have the X's and the Y. Okay. So you take some weight, you compute the Y from the X, and you look at the error that you have, and then you change the weight in order to minimize the error. So it's an optimization process. Okay. Okay. Of course, the weight.
Thank you.
Say it again.
Okay, thank you. Continue. Thank you.
Okay. So of course, depending on the data that you have, you're going to get, in this case, different weights. And so what you want is to have something that is general enough. And so one way to test that is to check the predictive power. And one way to do it is the so-called cross-validation. So typically, if I have a bunch of data, which is here, I'm going to divide it in chunks. In this case, it's 5 chunks. And I'm going to use everything to train, but the blue part. So the yellow part is used to train, and the blue part is used for testing. And then I change the blue part. You see here, I take either this part to test, either this part to test, this part to test, and the rest to train. And if in all the cases I get something that is reasonable, then it means that on average it's working. So this is called the cross-validation. And in this case, it's called the 5-fold, because I divided my data into 5. This is a 5-fold cross-validation. So typically we use 10 or 5-fold cross-validation. Of course, the more you give degree of freedom to the model that you use, the more you can fit the training. But then you may lose in generality. So the idea is the following. If I have these bunch of points, if I don't give enough degree of freedom, I'm going to fit maybe all these data by a line like this, which is clearly underfitting. So I'm going to make a big error, both on the training and for the validation. If I increase the degree of the polynomial here, for my training, I can make the error as small as needed, because in the end, I can end up with something that goes through all the points if needed, okay? But the problem is that when I try this on the validation part, then the error at one stage is going to increase because I'm not capturing the main thing, but I'm capturing details that are irrelevant on average. And so what you want to be in, so you want to avoid this overfitting region, you want to be in a sweet spot in which you have the minimum in the validation of error. Okay? So this is the way you have to do this. There are some packages online. There's some echo. Someone has his microphone unmuted, and I hear myself, and that's a bit annoying. If you could mute your microphone, or that would be nice. Yes. Okay. So in principle, you should hear me. Okay. So I continue. So, and there are tools online to do all this procedure automatically. In the framework of MathMiner, they have developed something which is called AutoMathMiner. That is a tool for automatically creating a bunch of models for your data. Okay. And so it's doing some stuff like random forest. There's many different things that are possible. And so if you want to start from something, I would advise you to use this because that does already a good job. Okay. Now, the predictive power of the model depends on the amount of data that you have. So if you have a small amount of data, usually it's better to use the so-called traditional machine learning because the neural network, as you have seen, they have plenty of degrees of freedom. So you need an important number of data to be in a good minimum for those weights that you asked about before. And so depending on the number of data, you may want to start by this traditional machine learning. But if you have more data, of course, you can go into a more complex model. So for instance, you can use neural network, and depending on the amount of layer that you put, you have the so-called deep neural network. And in the end, you can even have the so-called graph networks. And all these two, require more data than the traditional one to achieve good accuracy. And then, of course, when you have more data, they start to be better than the traditional one. Okay. So basically, you have to test quite a lot to decide what's the best thing that you need to do. So because of this basically difference with something which is simple but has a limited accuracy, that works with a limited amount of data, but you quickly plateau compared to things that are more demanding and require more data, we try to develop something different, which is called the material optimal descriptive network. The idea is to use a neural network, but in this case, we will deal with a neural network with few data, because the typical example that we had in mind were those phonemes, where we only have 1,500 data, so not very many. So in principle, the neural network will have a hard time there. And so our idea was to say, okay, rather than having a neural network with very, very many features, so typically with MathMiner, you can have several thousands of features, okay? The idea here is to do beforehand a feature selection. And the feature selection is based on relevance and redundancy. So the idea is to put prior physical knowledge and some constraint by adopting some physically meaningful features. So the features are selected automatically, but they are meaningful. That's the idea. And we get rid of all those that are not very meaningful. And this reduces the optimization space without relying on a massive amount of data. Furthermore, as I will show you, we have a novel architecture that allows to learn on multiple properties at the same time. So the first thing that I pointed was the relevance. Because of course, if I have a target, so my Y, and an X here that basically are connected like this is not a very interesting feature because there is no correlation between the target and the feature. In contrast, something like that where there is, some kind of clear dependence from the target on the feature too is really nice, because then I can quickly obtain a good approximate of the target just based on this feature. Okay. So one way to measure this interrelation between the feature and the target is the so-called Pearson correlation that I was mentioning before. And you can start from a perfect correlation, which is measured by this coefficient, which is 1 in this case. It can still be a positive correlation, but with more noise. So you would get a coefficient that's 0.9, 0.5 to something that is no correlation, in which case you have R0. And then you can end up to a negative correlation passing through something which is -0.5, -0.9, or -0.1, okay? So this measures the degree of interrelation between two variables. The problem with this coefficient is that this, if I have these data, so my x's are this and the y is this, you see that these two data are clearly uncorrelated, that's fine. So I have got r equal to 0, but a perfect parabola like this also gives you r is equal to 0. So the Pearson correlation coefficient has been made mainly for linear relation. As soon as you have nonlinearity relation between the x and the y, then you're screwed with this Pearson correlation. So we decided to use, for the feature selection, the so-called normalized mutual information. So what is the mutual information? If I have two random variables, it is a measure of the mutual dependence between these two variables. It quantifies the amount of information, which is also called the entropy, that can be obtained about one variable when you know some stuff about the other one. So for instance here, the red part is everything I know about this first variable x. The blue part is everything I know about this variable y. You see that there is a part that is common to both. So if I know y, then I can know all this about x, okay? And so the normalized mutual information is this region here in purple, which is this MIXY, that I divide by everything I know about x plus everything I know about y, okay? And of course, you have something in which there is no mutual information that's going to give you a 0, and something in which the two circles here overlap to give something which is perfectly purple, that would give me a 1 because the MIXY, which is the common region here, is going to be exactly the same as the blue and the red, okay? So this is this mutual information. And so that gives me information about the interrelation between a given variable and another one. So if I select the first feature as the one that has the highest normalized mutual information with the target variable, that's basically getting to something like this, where see, I have a strong interrelation between the target and the feature, be it linear or not, because I chose this normalized mutual information, okay? So that's the choice of the first feature. And so basically that tells me what are the variables that are very important in terms of explaining my target property, okay? So for instance, in the case that I'm interested in, this vibrational entropy, I can show, based on this choice of the normalized mutual information, that the vibrational entropy is strongly related to the interatomic bond length and also to the valence range of the constituent. So of course the length, the longer the length, the weaker the bond, okay? And then the second point here is the valence range of the constituent. If you have two elements that are strongly ionic, you're going to get a stronger bond. So you see that here, this is my vibrational entropy as a function of this feature here, which is nothing but the interatomic bond length. You see that when I increase the bond length, I decrease the entropy, okay? But then I have colored also the second feature here, which is the valence range. And you see that there is a strong dependence. You go from purple here at the bottom to yellow at the top. You see, if I plot the S as a function of this one, I would also add a trend, okay? So the next thing that I want to do is that once I've chosen my first feature, I want to avoid redundancy. If I have another feature that is strongly related to the first feature that I chose, it's not going to bring new information in my model. So I want to avoid that, okay? And so we take that into account to choose the successive features. How do we do that? Is that we want to maximize the relevance of the feature while avoiding redundance. And so we have defined relevance redundancy score that is based on the mutual information that you have from the feature to the target, but we want also to minimize the redundance, and so we want to minimize the mutual information from the feature with all the other selected features, okay? So basically you have this form here, this fraction here, with two coefficients P and C. Typically, if P is equal to 0, you're maximizing the mutual information. Sorry, if P is, if P is 0, indeed, you're maximizing the mutual information between the target and the feature. Then if P is not 0, then you pay attention to the redundance. Ideally, you need to vary dynamically the P and the C because it works better, and the redundancy is a bigger concern when you have a small amount of features. But so we have a formula for the P and the C that we suggest to use this model here. And then the selection proceeds. So once you have few feature, you can add new ones by maximizing this relevance redundancy score until you reach a given threshold on the model error. So either you optimize that or you say, okay, I want 1000 feature and that's it, okay? So this is the way in which you would select the feature. The second thing that I said was that we have a way to optimize several properties simultaneously. So basically what we do is that we have the first part of the neural network that is common to all the properties that we are interested in, and then we group the properties precisely by group, depending on what they are referring to. For instance, it can be vibrational property, mechanical property, electronic property, and so you have groups of properties which can be further subdivided until you reach a given property that can depend on the parameter A. So for instance, the entropy here can depend on the temperature. So you can have the entropy at different temperatures. You can have the specific heat at different temperatures. And so if you learn all together, all these relations, that further improves the results that we get, okay? So just to show you what we get, I'm coming back to my problem here. So for which we had 1,500 calculation of the entropy at different temperatures. And we use that to try to predict the entropy by using machine learning. So we were not the first one to do that. And actually this blue cross here is a previous result that had been obtained a few years ago for about 300 materials. And so that's a random forest that is based just on the composition. So there's no information about the structure. So this is what you get as a function of the training side. See that the more data points you get, the more accuracy you get until you reach a certain plateau, okay? If you include information about the structure, you see that you further reduce the error that you make on the entropy just by taking the information about the structure. You know, like I showed before, it can be the space group, it can be the local environment, stuff like that. If you include all that, you can, using random forest, you can get a very good accuracy. If you use magnet that I showed you before, you get the pink curve that you have here. And if you use the modnet that I just explained, so the one that takes into account, so it's a neural network that uses relevance and redundancy score to select the feature, so this is what you get, okay? If you use a neural network, but without feature selection, this is what you would get. So that's the orange part. So again, we have the modnet, the magnet, with our modnet, which is better than the magnet. But if you had done no selection of the feature, you see that when you have not very many data, the result is quite worse than what we can get when we do the feature selection, okay? And finally, if you take into account multiple properties, you can get a slightly better accuracy. You see that most of the time the green curve is better than the purple one, but also we have a single neural network that gives you all the properties at the same time. And so that's what we did, that we used that to predict the thermodynamic properties such as the entropy as a function of temperature. So here what you see, the solid line provide you the different thermodynamical properties that we computed ab initio, so that's the solid line, and the dashed line is what we have learned from machine learning. In most of the cases, and when I say most, it's like 90% of the cases, we get a very nice agreement like here, here, and here. In some of the cases, we get something which is a bit worse, but still, this is very good to make predictions and to make selection. The only thing that we have to pay attention to is to be aware of the error that we're making, because when we're comparing different polymorphs, see that the order of the polymorphs may change with temperature when we take into account the entropy that is taken from machine learning. But you have to pay attention in a region in which there is small difference between the different data, because of course there's an error bar on each of the points because of the machine learning. Okay. Now I'd like to show you one last example in which we have computed the refractive index for materials. So basically, we'd like to have a bunch of materials, again, with two contradicting properties. We'd like to have a high refractive index and a high band gap. We want a high refractive index for some materials because we have in mind some optoelectronic devices and we want to improve the performance. And also, we would like to increase the response in the nonlinear regime. And it can be shown that this nonlinear response is related to the refractive index. And also, we'd like to have a high band gap because it guarantees transparency in the visible spectrum, and it allows the device to operate at higher temperature and to switch at larger voltages. So as I said, we can do calculation with the DFPT again to compute the refractive index and use the DFT band gap to get an idea. And as I said, these two properties are kind of contradictory in the sense that there is an inverse relationship. When you increase the gap, the refractive index decreases. So we did calculation like this for 4,000 compounds, and these are the gray points that you see here. For all of them, we did a DFPT calculation. So we have a database with 4,000 data points. In the past, people had come with some empirical relationship, which they basically got. So it can be this line here. It could be things like this, which are a bit more evolved, things like that, like this, so on and so forth. But this is not very satisfactory. And to be fair with the guy that developed this empirical model, is that they obtained those based on a limited number of points. And so, of course, they cannot take into account the huge amount of points that we obtained, well, the quite big amount of points that we obtained here with 4,000 points. So in the previous paper, we had developed a physical model, which we published in 2019, about how this dispersion here, so for a given band gap, there's a spread in the refractive index that you can get. We explained that thanks to a model, but what I would like to show you here is that thanks to these 4,000 data points, we could compute the refractive index from the complete materials project without doing the DFPT calculation, just by the machine learning. So when I mean compute, it's like a second, okay? And thanks to that, we can look at materials that have a rather high band gap while still having a large refractive index. And basically, if you want, we can do in the funnel that I showed in the beginning, we can have a layer that is based on machine learning to select some materials. And just to be sure, we can do the DFPT calculation on those. And that's what we did for a bunch of materials. You see, the results from the machine learning was this, and this pushed us to do a DFPT calculation. And as you can see, the error is quite small. And so we have a prediction of the refractive index that is enough to screen material. And so with this, I will conclude. I think that I've shown you that by using ab initio computing and machine learning, we can discover different kinds of materials with specific properties that we have in mind for a given application. And finally, I'd like to thank all my collaborators on these projects. So at UCLouvain, there's Pierre-Paul de Breuck, Nicolas Dardenne, Francesca Naccarato, Guillaume Brunin, Guido Perfetto, Francesco Ricci, David Wautier, Matteo Giantomassi, Xavier Gonçalves, Jean Fautier. And then at Berkeley, there is the group of Anubhav Jain, Gert Cedar, and Kristen Persson. And finally, in Santa Barbara, there's a group of Shui Qingdong that I would like to thank. And finally, I'd like to thank you all for your attention. Thank you very much.
So thank you very much, Gian-Marco.
Thank you.
So this was very good. So we'll take questions. Does anybody have any other questions? You can unmute your mic and then ask the question. Yeah, so you can ask your question.
Yeah, my question is, can you hear me?
Yes.
Yeah, my question is, you talked about reducing the dimensionality of the points using the feature extraction. Is it trying to, is it applying the group theory?
No,
because the diagram you showed looked like a block diagonalized matrix.
There was just an example. So that's just an example. So, okay, this, I guess that you're referring to this diagram here. Just a second, this one, right?
Yeah, where you make mention of.
Yeah, so basically this here refers to an image. So basically what you see here is the piece of, you see the digital prints. So it's a piece of this, which basically consists of 1 and 0.
Okay.
If you take it too precise, it's this. But I mean, if I take another piece here, it would not be a diagonal thing. It would be something which is maybe like this, or the other way around, or completely different. It depends which piece of the picture here I'm taking here, okay? So as I said, and as I showed, that the feature extraction in the case of relevance redundant. So first of all, we have here a bunch of features that are coming from Math Minor. Typically, as I said, you can have 50,000 features. So it's a very high dimensionality in that case. And the way we do it is that we use to make this feature extraction, we use this relevance redundancy ratio that I showed here, okay?
Okay.
So this is how we proceed here.
Okay, which means that you are not, you didn't apply any group theoretical methods in your work?
No.
Okay.
Apart from knowing what is the space group of the material.
Okay.
But that's not even necessary. I mean, you do with what you have. If you don't have the space group, then you don't consider the space group, okay?
Do you have any other questions?
No other question for now. Thank you.
Thanks.
Yeah, I have a question.
Yes.
Go ahead.
Yeah, I have a question. My question is on how is it possible for us to really tell for a given model that you choose and you use that, how possible is it for us to differentiate from when the model is has actually learned and whether the model has just memorized our data, and then when you want to generalize it fails in application of some data that you have not used.
Okay, I'm not sure that I understood everything because the quality of the line was not very good.
Yeah, Sunday, can you type your question or repeat? Yeah,
But
if
I
you type.
I kind of understood. I'm not sure. I'm going to say what I. So.
Okay, my question.
How do you know whether the model, the machine learning,
the question is,
or it's actually learned? Yeah.
Has it learned or
so
just memorize your?
Well, I mean, okay, if we're speaking about a neural network, it's not memorizing anything because basically it's defining the weights that you have there in the neural network that I was showing before. So this is not, a memory in any case, okay? The only way that you have to see whether it works or not is just doing calculation on a training set, a validation set, and a test set. And you need to find this position here in which your validation error is minimum, okay? And then you know that basically you have learned some stuff. And in principle, if you test something, you should, that's another way to check that you learned something. I mean, for instance, if I go back to this example of the refractive index, basically what we did is that we applied the model that we got, and these are the blue points here. Okay, this is the machine learning result, okay, which is very fast. So we train the model on the red point, we get the blue point very fast, we select the ones that are interesting for them, and we check that it works by doing either an experiment or, in our case, a DFPT calculation. And we see that the error that we predicted based on our model and the cross-validation is reasonable compared to what we have here. You see that there are cases in which the error is very small, some other in which it's bigger, but still, I mean, 2.6 respect to 2.8, I'm fine with that to do. Remember that the only thing that I want to do is to do a funnel, okay? So I can clearly identify the interesting material. I don't have something which I predict by machine learning to be 2.5, and then it's 1 or 5. You see, the error is very small.
Okay. Any other questions?
I would like to ask a question with respect to GW calculations. So I want to know, of course, while we do GW, we would have to do ab initio calculations first. So I'd like to know if we do LDA first or we do GGA first for our GW calculations. So which will you advise?
I mean, it doesn't really matter because the gap is not very different in LDA or GGA. So you choose whatever. So basically, I mean, so for instance, if I go back to my funnel here, if I find it here, if I go back to my funnel here, you see, I want to have a wide band gap. And I know that DFT is usually, you know, underestimating the band gap, okay? Yeah. So typically you could have here a first screening layer that says, oh, I want a band gap that's bigger than, I don't know, 1 or something like that, because I know that if I'm bigger than 1, then most probably DFT, the final result is gonna be bigger. So I can already remove a bunch of materials from that. So that's a PBE or LDA calculation, and then leave the GW for a later stage in which then I make sure that I have a prediction that is more accurate. So never hesitate in this funnel approach to compute the same property with different levels of accuracy, just because you can remove materials at one stage, and that helps you to go with a lower number of materials. Okay.
So for GW, then it doesn't matter whether you do LDA or
no, it doesn't make a big difference. I mean, if you compute the gap between LDA and PBE, I mean, the main difference is going to come from the lattice constant that is changing. Otherwise, the gap is, I don't know, the difference between LDA and GGA is maybe 0.1, 0.2 EV. I mean, that's not the kind of accuracy that we can pay attention to.
Okay.
You always need to be careful about, I mean, the whole idea of these funnels is to try to reduce the number. So if I go back to what I was showing here, so if I show this here, I mean, what you want is that at the end, you provide a number of candidates to your colleagues that is reasonable. You want, I don't know, 10 to 100 of compounds, because then you can convince them to try to synthesize the material. You don't want to say, oh, the property is going to be, you know, I don't have the precise value of the property. I just can say, oh, I have a material that should be interesting, okay?
Okay.
So typically 10 to 100 of compounds.
Okay. So Gian-Marco, let me ask this question. So there was a slide you showed where you showed that then the entropy increases as the bond length decreases, right?
Yes, yes.
So this is something one would think is reasonable, right?
Yes.
Like, okay. So is it possible to come up with many of these rules from doing machine learning?
Of course, of course.
Like the second one that you wrote, the valence range of the constituent element.
Yes, yes.
That's hard to just guess. Okay, but the first one, think about it and say, okay, that makes sense.
Yeah. I mean, so there's a lot of stuff now. Okay, so when you do neural network, or even random forest, it's sometimes difficult to interpret the result. Okay, especially for neural network. And so now there is more and more work that's being done in machine learning to try to understand the outcome of the machine learning.
Okay.
Because, I mean, okay, there's an approach that is called CISO. I don't know if you guys know.
Yeah, I was going to ask you that. I was going to ask you that. Yeah, go ahead.
Okay, so CISO, basically this approach, it's providing you a formula in the end, okay?
Yeah.
But it's quite demanding in terms of calculation. Actually, we have submitted this paper for publication, and one of the referees, maybe you, asked about CISO. And so we've been doing CISO calculation for this very problem. And I can tell you that CISO, basically, if I were to show you, let's see, where are the curves here? Yeah, here. So typically, if I compare CISO here, it's something that's like that. So it's, I mean, something like this, if I'm not wrong. Sorry, it's like this. It saturates quite fast. Yeah, I should show it here. If I show it here, in the beginning, it's reasonable. It may be even as good as Magnet, but then it saturates.
Oh, okay, that's right.
So, and the nice thing about CISO is that it provides you some very important features. So in terms of interpretation, CISO is very nice. Okay.
Yeah, although some of the formulas is just hard to comprehend.
Yeah,
because
because I mean the philosophy of CISO is that all the non-linearity is put in the choice of the feature. So basically what you do is you start from some features, but then you mix them. In the sense you can do the product of two of them, the logarithm of one, you can do
whatever.
Yeah. And then once you have these new features which are a mixing of the previous ones, then you do just a linear regression. So all the non-linearity is in the first part. And so indeed you can end up with some weird formula that's not always very nice either.
Okay. Thank you very much. If there's any question, we'll take them. But what I want us to do is to maybe form like 2 or 3 groups together. So if you're so once again, we thank Gian-Marco for the seminar. So we finished
sharing maybe.
Yeah. So thank you for the questions also, and I hope I'll collect the slides from Gian-Marco, and then we'll put it in a place where everybody will be able to access it. The video also will be put online. Okay, I should stop recording now. So what I want us to do